Welcome to Edupedia World Grade 10 Computer Science Video Lecture Series. I'm Upeka Vendibona, and this is the third part of Numbering Systems Conversions. From the previous two episodes, we cover up everything regarding decimal numbering systems. Binary to decimal, binary fraction to decimal, decimal to binary, and decimal fraction to binary, and same thing with the octal numbering system as well as the hexadecimal numbering system. So I hope you are now familiar with decimal conversions. From this episode, we are going to learn other type of conversions among binary, octal, and hexadecimal. We are not going to touch up every little bit in here because everything have the same pattern as we learned in the previous episode. So we are going to mention only the important things that you need to make the conversion very much easier. So let's start with binary to hexadecimal. You already know binary have zeros and ones, and hexadecimals have 0 to 9 and A to F. So here we are given the binary number 1000101. This is a binary number. We have to convert into a hexadecimal number. So how to do this? If this is a decimal number, then we know to convert a decimal number into a hexadecimal value, we have to divide it by 16. But this is a binary number. If binary number needed to be converted into a decimal number, then we know we have to create that table structure with the 2 to the power of n values. But here we are converting binary to hexadecimal. So this is a totally different process than the decimal numbering system. So this is how we are going to do that conversion. The first step is creating groups in the binary value. We have to start from the rightmost position, and each group should contain 4 bits. So the first group is 0101. So after the first group, 3 bits are remaining. Therefore, to make it 4, we have to put the 0 in front of the value. So the second group is 0100. Okay, now the next step is converting each of these groups into its equivalent hexadecimal value. For example, if we take the first group 0101, it is equal to 5, because in the rightmost first position it represents 2 to the power of 0, in the second position 2 to the power of 1, in the third position 2 to the power of 2, and the fourth position 2 to the power of 3. So it equals to 1 multiplies by 1 plus 4 multiplies by 1 equals to 5. So likewise for the second group 0100, it represents the value 4. So if we take both of these values 4 and 5, that is the hexadecimal value of our binary number. So this is how we convert binary to hexadecimal. It is a grouping activity. Now let's move on to the next conversion type. It is the conversion of binary fraction to hexadecimal. So in the given number, we have a binary point 11100.1010. So like as before, we have to create groups with 4 bits. For the integer part, we have to start from the rightmost position. For the fractional part, we have to start from the leftmost position. So for the fractional part, we can create a 1 4-bit group 1010. For the integer part, the first 4-bit group is 1100, and thereafter a 1 bit is remaining. So to complete a 4-bit group, we have inputted 3 zeros in front of that 1 bit. So the second group is 0001. So now we have to convert each of these groups into its equivalent hexadecimal value. The fractional part group represents the value 8 multiplies by 1 plus 2 multiplies by 1. This is equal to 10. So in the hexadecimal numbering system, we doesn't have the value 10. We have the character A. So this group represents the character A. In the integer part, the first group is 1100. So it represents 8 multiplies by 1 plus 4 multiplies by 1. It is equivalent to 12. So in the hexadecimal numbering system, we doesn't have the value 12. We have the character C. So the first group in the integer part represent the character C. The second group is represent the value 1. So the final hexadecimal number is 1C.A. So this is the hexadecimal value represented by the given fractional binary value. Okay, now the next conversion activity is hexadecimal to binary. For that, we are given the hexadecimal value 10AF. We have to convert each digit of hexadecimal number to its binary equivalent and write them in 4 bits, and thereafter combine each of these 4-bit groups into a one resulting binary value. So that's how the conversion process is going on. Now let's take our example 10AF. The first rightmost position character is F. If we convert this F into a binary value, we can get 1111. Because the hexadecimal character F represents the decimal value 15. To convert a decimal value into a binary equivalent number, we have to do that division by 2 process. If we input this 15 into that division by 2 process, we can obtain this 1111 binary value. Same thing goes with the second character A. The character A represents the decimal value 10. So if we convert this decimal value into a binary equivalent number, we can obtain 1010. If you want to check the validity of that binary value, you can do that too. So here 1010 means 8 multiplies by 1 plus 2 multiplies by 1. It is equal to 10. So our representation of the character A is correct. Now the third digit is 0, and when we are making groups, we have to make sure that each group have 4 zeros. So rather than having a 1 0 in here, we have to put 4 zeros. The next digit is 1. So here the binary representation is 0001. So by combining each of these groups together, we can obtain the final answer 000100010101111. As to practice the conversion of hexadecimal to binary, let's take this example A to F. It is a hexadecimal value. We have to convert into a binary value. So for that, take each of the digits in the hexadecimal value A to F. But we cannot convert if we keep these values in this form. We have to convert these things into its equivalent decimal form. That means A equals to 10 and B equals to 11 and C equals to 12 and D equals to 13 and E equals to 14, and here F, it is equal to 15. Now 15 means the decimal 15. If we divide it by 2, we can obtain the quotient 7 and the remainder is 1. If we divide the quotient 7 in 2, the quotient is 3 and there is a 1 remainder. If we divide 3 by 2, we can obtain the quotient 1 and the remainder is 1. So this is the binary equivalent of the decimal value 15. So here 1 1 1 1. Now 2 means 0 0 1 0, because this position equals to 2 to the power of 0, this position equals to 2 to the power of 1, that means 2. So this is the binary equivalent of the decimal 2. Now in here the character A means 10. That means we have to convert this 10 into its binary equivalent. The quotient is 5 and the remainder is 0. Quotient 5 should be divided by 2 and the quotient is 2 and the remainder is 1. If we divide the 2 by 2, the quotient is 1 and the remainder is 0. So the binary equivalent of the decimal value 10 is 1010. So here it is 1010. So the final answer is 101000101111 and the base 2. So this is the binary equivalent of the hexadecimal value A to F. Now the next one, hexadecimal fraction to binary, is same like this process. you have to convert each of the digit in the hexadecimal value to its equivalent binary form, and each time for each group it should exactly contain 4 bits. So it is the same process. Therefore, we are not going to show you how the hexadecimal fraction to binary conversion process is going on. We are going to skip that part and move into binary to octal and octal to binary. Now in here it is the same process as we did in binary to hexadecimal and hexadecimal to binary, but the difference is in here for each group it has only exactly 3 bits rather than having 4 bits. In here it has only 3 bits. Let's take this example octal number 742. To convert this into a binary equivalent number, take each digit of the octal number 742 and convert them into the equivalent binary number. So for 2 it is 010. Here in this group it has exactly 3 bits. For the second group, the number 4, it represented by the binary value 100. The third group, the number 7, it represented by the binary value 111. So the final answer is 111100010. Now that is the octal to binary conversion. For the binary to octal conversion, the first step is group the given binary number. And for each group, it should exactly contain 3 bits. And also when grouping, you should start from the rightmost position. And after grouping, you should convert each of the group into its equivalent octal number, and finally combine the group result to obtain the final octal number. So there is no big thing in this conversion too. Now you may be wonder why it is all about grouping. For the hexadecimal it is grouping with 4 bits, and for the octal it is grouping with 3 bits. Now what is that? If we represent the base of the octal numbering system in the form of power of 2, it is 2 to the power of 3. And if we represent the base of the hexadecimal numbering system in the form of power of 2, it is 2 to the power of 4. Due to this reason, we can take the bits into groups of 3 and represent each group as an octal digit, and take the bits into groups of 4 and represent each group as a hexadecimal digit. That's the story behind grouping. And with that we have covered up all the relationships the binary numbering system have with other numbering systems. Now the remaining ones are the hexadecimal and octal. We first take the conversion of hexadecimal to octal numbering system. We are given the hexadecimal value A42. As the first step, convert each digit in the hexadecimal number to its binary equivalent. When you write it, make sure that each digit conversion have exactly 4 bits. And after that, combine all the results and starting from the rightmost position, group it. When you group it, make sure each group have exactly 3 bits. And finally, convert each of the group to its equivalent octal number. The combination of this final result is the answer. So in this example, 2 is represented by 0010, 4 is represented by 0100, and the character 8, which means the value 10, is represented by 1010. Those are the 4-bit groups. Now we have to combine these 3 groups and create 3-bit groups starting from the rightmost position. So the first group is 010, the second group is 000, the third group is 001, and the fourth group is 101. Now each group should be converted into the equivalent octal number. The first group 010 is 2, the second group 000 is 0, the third group 001 is 1, and the fourth group 101 is 5. So combining this last result, we can obtain the octal number 5102. So this is the process of hexadecimal to octal conversion. If you are given a hexadecimal fraction value, it is a not big deal. It is the same process. The only difference is when you are creating 3-bit groups, for the integer part you should start from the rightmost side, and for the fractional part you should start from the leftmost side. So it is same like the hexadecimal fraction to binary conversion. As there is nothing much new to show you, we will skip hexadecimal fraction to octal conversion and move into octal to hexadecimal. In here we are given the octal number 762 and we have to convert into the equivalent hexadecimal value. So the first step is converting each digit of the octal number to its equivalent binary form. When you are writing the equivalent binary value of each digit, it should be exactly in 3 bits. And after that, all those 3 bits groups should be combined, and starting from the rightmost position, you have to create groups again. And this time each group should contain 4 bits. And finally these 4 bits group should be converted into the equivalent hexadecimal value. And remember, when the converted value is more than 9, it should be presented with the relevant English character. Now take a look at the example. The number 2 is represented by 010, the number 6 is represented by 110, and the number 7 is represented by 101. Now the next step is combining these 3 groups and starting from the rightmost position, creating groups again with 4 bits. So the first group is 0010 and it is number 2. The second group is 0111, it is represent the number 7, and the third group is 0001, it is represent the value 1. So the equivalent hexadecimal value is 172. So this is how the octal to hexadecimal conversion process is going on. I am not going to talk about how the octal fraction to hexadecimal conversion is happening because it have the same process. The only difference is for the integer part you should start from the rightmost position for the grouping, and for the fractional part you should start from the leftmost position for the grouping. As now you are very much familiar of that kind of a thing, I am going to skip that and move into the summary of what we did in all these 3 episodes. In the previous 2 episodes, we learned all types of conversions regarding decimal numbering system. Binary to decimal, binary fraction to decimal, decimal to binary, decimal fraction to binary, decimal to octal, decimal fraction to octal, octal to decimal, octal fraction to decimal, decimal to hexadecimal, decimal fraction to hexadecimal, hexadecimal to decimal, and hexadecimal fraction to decimal. In this episode, we learned the other type of conversions. For example, binary to hexadecimal, binary fraction to hexadecimal, hexadecimal to binary, hexadecimal fraction to binary, binary to octal, binary fraction to octal, octal to binary, octal fraction to binary, and also the hexadecimal to octal, hexadecimal fraction to octal, octal to hexadecimal, and octal fraction to hexadecimal. And in this episode we have also identified that the binary numbering system and the decimal numbering system plays an important role. For example, for the hexadecimal to octal or octal to hexadecimal conversions as intermediary steps, we have used the binary numbering system and the decimal numbering system. So with that we are going to end up this episode. I hope you got the clear understanding on how to perform any kind of a conversion among the binary numbering system, octal numbering system, decimal numbering system, and the hexadecimal numbering system. From the next lesson, we are talking about binary representation of the integers. Thank you for watching and stay tuned on with Edupedia World.